All right, this first question has us looking at a reaction between magnesium metal and aqueous solution of hydrochloric acid to produce hydrogen gas and magnesium chloride. We've actually done this before in lab. We've worked with zinc and hydrochloric acid to make hydrogen and zinc chloride. But basically, the question is, which statement about this reaction describes what you would see if you did this in the lab? So a couple of things to take note of in particular are the phases that these chemicals are in. That's gonna really help you out when you answer this question. So magnesium solid, aqueous solution of hydrogen chloride, which is hydrochloric acid, and then this gaseous hydrogen gas, and a solid formation of magnesium chloride. So let's just go through these options and see which one best describes that. So A is two gases react to produce a solid substance. That can't be right because we've got a solid and an aqueous reactant. So A is out. A solid is reacted with a liquid or solution of some sort and bubbles are produced. That sounds pretty promising because we've got our solid and a liquid, which hydrochloric acid is not a liquid, it's an aqueous solution, but maybe if you were just looking at this in lab, you would call it a liquid, I suppose. And when those react, bubbles do get formed. So the bubbles are formed, that's hydrogen gas. I think B is a pretty solid contender. And then C, two solids react. That can't be right because hydrochloric acid is not a solid. And finally, D, a liquid and a solid react. Oh, that sounds good. And then two solid products are produced. But that's not right, is it? Hydrogen gas is a gas. We do have a solid, magnesium chloride. But the only one of these answers that really works is answer B. Okay. Number 2, label each of the below chemical equations as synthesis, decomposition, single replacement, double replacement, or combustion. These are the 5 reaction types that we learned back in the beginning of Unit 5. And this just has to do with what is reacting and what's being produced. And so there's some patterns to look for here. This one here is a synthesis reaction. And synthesis reactions basically occur when you have multiple reactants and then only a single product. So we've called these combination in the past. We've called those combination reactions just because we're combining things to make a single product. So go back in your notes, take a look at that stuff. This next one, zinc solid plus copper 2 sulfate in an aqueous solution to make zinc sulfate and copper metal. This one is what we would call single replacement. And that's just because the metals, zinc and copper, they are just making a switch to become 2 new products here. This is also an oxidation reduction reaction where the copper has been reduced and the zinc has been oxidized. But think of that as a single replacement. This next one, this is where we have 2 binary ionic compounds that react. Excuse me. This one's actually a we would call it precipitation reaction, but we're going to label it as a double replacement. And that's because the sodium and the silver, as you can see, switch partners. Remember, this is where we would say the outside ions connect with the outside ions and the inside connect with the inside. And so we've made sodium nitrate, which is from sodium in one reactant compound and nitrate in the other reactant compound, and silver and chlorine to make our new products. So we've got 2 replacements of the metal occurring there, and that's why we call it double replacement. Next one here, we would label this one as a decomposition. And decompositions are just, they're very similar to synthesis reactions They just are the reverse of a synthesis reaction where instead of a couple of reactants forming one product, we've got one reactant decomposing, breaking down into multiple products. That's what decomposition is. This one, this last one here is called a combustion reaction. And this is the combustion of a hydrocarbon or of a carbohydrate. This is a hydrocarbon example because we just have a hydrocarbon compound here. But in all of these reactions, what you can always expect to see is some sort of a hydrocarbon, which is made from hydrogen and carbon, or a carbohydrate, which is carbon, hydrogen, and then there'd be an oxygen component to that chemical. But regardless, it's one or the other, and oxygen gas, O2. And the important thing to remember about this is the products of these reactions. The products of a combustion reaction, at least on paper, the way it's supposed to go at least, is that in any combustion reaction, we should only be making carbon dioxide and water. Okay, it doesn't always happen like that in real life, of course, but on paper it should. So those are the 5 types of reactions you should be familiar with and be able to recognize. All right, number 3. What are the products when copper 2 nitrate reacts with iron? So this is going to be a single replacement reaction between CuNO3, that's copper 2 nitrate, and iron. So in a single replacement reaction, all we're doing is basically switching places. The iron and the copper are going to swap places, and we're going to make iron Fe, and this usually forms Fe NO3, 3. The oxidation state +3 is always the most common for iron, and copper. Copper gets reduced to elemental copper. So just be familiar with the mechanics of the single replacement reaction. You won't have to guess at what the oxidation state of a metal is going to be like I did here, but just know the pattern. Okay, number 4. A solution has a hydrogen ion concentration, that's what this H plus in the brackets means, right, of 3.4 times 10 to the negative 4th. What is the pH of the solution? So that's where we're going to use this diagram that we've made in class, and it's in your notebook. And this just is sort of a roadmap of a couple of different functions on your calculator that are going to allow you to move between pH, POH, hydrogen ion concentration, and hydroxide ion concentration. And so let's just think of where we're starting. We've got our hydrogen ion concentration, which is this value here, and we want to know what is the pH of that solution. So we follow the arrow, and we're just gonna do nothing but type in negative log and then 3.4 times 10 to the negative 4th in the calculator. And that looks like this. We're going to go negative log 3.4 times 10 to the power of negative 4, close that parenthesis, and equals. And we should get a pH of 3.47, we can call that. So I'll just do what we did here. We did negative log of 3.4 times 10 to the negative 4th. And that gave us 3.47. And that's good. pH values are always going to be, within between 0 and 14. So if you end up with something under 0 or above 14, you've done something wrong. But 3.47 is a totally reasonable answer here. Okay, number 5. Which of the following is an acid-base reaction? Okay, so in this one, remember that in our acid-base reactions, we look for either Arrhenius acid-base stuff, which has to do with H and OH stuff, That's what this one is aiming at, by the way. Oh, and the other one is going to be some Bronsted-Lowry acid-base work, which we'll get to later in this practice test. So really what we want to go through here, we want to go through and look for not only reactant compounds that have hydrogen or hydroxide ions, but we want to look to the reactants and see that we've made water and some sort of salt. That is an acid-base neutralization reaction, and that's what we're looking for in this problem here. So let's just take it from the top and see which ones are which. So this first one seems pretty promising right off the bat. We've got our hydrogen and our hydroxide components in our two reactant chemicals. This one is called, what is this called? Hypochloric acid? Either way, this is called calcium hydroxide, and the products here are water and then calcium chloride. And so that's a pretty good indication of acid-base neutralization right there. These other ones just don't really make much sense. Iron and silver nitrate, that's neither acid nor base. Carbon and oxygen, though that's not acid and base. And magnesium sulfate and barium nitrate, this is just a double replacement precipitation reaction. So the only one that makes any sense here is A. And again, I think what you really want to look for are H in one compound and OH in another compound. That means an Arrhenius acid and Arrhenius base, and we neutralize that to make water and some sort of salt. Okay?